Elliptical waveguides are analyzed using elliptic-hyperbolic coordinates because traditional Cartesian and polar systems fail to cleanly define the boundary conditions of an elliptical cross-section. Within these hollow metallic pipes, electromagnetic waves propagate as TE, transverse electric, or TM, transverse magnetic modes, both of which must satisfy the Helmholtz Wave Equation. By transforming the geometry so the outer wall collapses into a single constant parameter line, the Helmholtz equation separates into angular and radial Mathieu equations, allowing field profiles to be constructed analytically using even and odd Mathieu functions. These profiles must meet specific boundary requirements, such as Dirichlet conditions for TM modes, where the electric field drops to zero at the wall, and Neumann conditions for TE modes. Simulations of these fields demonstrate that as the waveguide's eccentricity is adjusted, the longitudinal electric fields and their associated closed magnetic loops conform dynamically to the shape of the pipe, ensuring that magnetic tracks remain tangent to the boundary wall without breaking field continuity.